Yeah, I just put it in the monitor. This is good.
Ah, okay, okay.
Okay, guys, I'm getting ready. Hello, everybody, and welcome to this week's Astro Coffee Hangout. My name is Tony Darnell from deepastronomy.space, and we do these every Thursday. These hangouts are sponsored and endorsed by the American Astronomical Society and the American Astronautical Society, and we'll get back to that in just a little bit later in the hangout. But I am very excited about today's hangout topic. Today, we're going to be talking about whether or not some kinds of dark matter may have an electric charge. Now, it turns out that the observations of the early universe from a radio telescope in Australia return some kind of confusing results. Looking at the first stars in the universe, it appears that the interaction between these stars and the neutral hydrogen and the cosmic microwave background might have actually shed some light, so to speak, from the radio telescope on dark matter, and some possible explanations that came from that data might indicate maybe that dark matter has, some of it anyway, has an electric charge. Now, while these results are still somewhat controversial, we're going to take a closer look at the observations as well as the proposed model for explaining them. Now, one of the things I just got to say that one of the things I really love about doing these hangouts with Carol is that as I saw this press release, I made an episode of Space Fan News to share these results to people on my channel, and I sent out a quick email to Carol that this will be a good hangout topic, and lo and behold, a few days later, we had it on the calendar. So I'm very excited to get going and share this all with you. And I want to welcome everyone watching live on YouTube, and so please take advantage of these hangouts by asking our guests questions live, and we also have a Discord server that you can chat on that with it's open 24/7. So if you go to deepastronomy.space/live, you'll see it there. And I also want to welcome those watching the replay of this, and please don't feel left out. Leave your questions in the comment section, and we'll still get around to answering them even though it's not live. And we also, of course, post the audio portion of this podcast on other platforms like Anchor and various other places. So look out for those on those platforms. Now, I just have to give a quick shout out to the undergraduate astronomy class of Professor Karen Masters of Haverford College in Pennsylvania. Her summer astronomy students are watching now. They watched last week too. They're yay! They're tuning in live. So welcome, guys, and again, ask your questions, and I'll make sure to read them. Okay, our guests today are authors of a paper that came out in Nature earlier this month, proposing a new model for dark matter that includes a tiny electrical charge that may be part of this annoyingly elusive stuff. So let me bring up everybody here. Let me bring up my little hangout here. And let me start by introducing my co-host, Dr. Carol Christian from the Center for Emerging Media. She's in the upper left here. Hi, Carol. Welcome.
Hello, nice to see everybody, and it's really because our guests were so prompt in getting back to me, which is good. I mean, yes or no, we just need to know, and it was fabulous that everybody said yes. So we're really very fortunate to have this team here.
That's right. So I want to also echo that. Thank you for
really enthused about this.
Yes,
hangout.
Okay, so let me just go. I guess I'll go in a clockwise motion. Next to Carol is Dr. Cora Dvorkin, and I guess you guys are all from Harvard University. In the lower left hand pane is Dr. Julian Munoz, and next to him in the lower right is Dr. Avi Loeb, who's returned. You might remember him from past hangouts. He did an ExoLife hangout with us a few months ago. So welcome, guys, and I guess we should probably start with the basics here, because the stuff we're going to be talking about is a little bit I don't want to say obscure, but we're going to have to pay attention here because there's a lot going on. We're talking about areas in the early universe. What did I say?
Obscure.
See, I do it and I don't even realize it. I just talk in puns. All right. So
Sorry.
Yeah, so I want to start with this idea of dark matter. Now, viewers of our channel I've known for a long time about dark matter. I'm not going to ask you what it is because the answer is nobody knows, but it is this stuff that's out there that won't interact with us in any way. And I guess I want to ask one of you, maybe Avi, you can comment on this part. Why is it that astronomers are so confident? Or maybe I should say, what is it that makes astronomers so confident that dark matter even exists if it doesn't interact with us in any way?
Well, the nature of the dark matter is one of the longest standing puzzles in cosmology. For nearly a century, the identity of this constituent of matter, which dominates the universe, remained mysterious. We know that it exists because it induces a gravitational force on ordinary matter. And so we know that ordinary matter moves in ways or emits radiation in ways that are different than if it were left on its own. There is some additional stuff out there that holds together galaxies, for example. And without that stuff, the galaxies would fall apart. There is not enough gravity in the ordinary matter to keep them bound together the way they are. We see the stars moving much faster than they would move if they were just self-gravitating, if they were just producing the gravity by themselves. So there needs to be more stuff. And this stuff is not emitting any light, and it's not absorbing any light. We can't see it directly with telescopes, and we call it dark. Okay, and this was the name. Dark matter was coined about a century ago. Franz Zwicky was the first to detect strong evidence for its existence in groups of galaxies, clusters of galaxies. And then after Zwicky's observations, there were decades where additional data came in, mainly in galaxies, the dynamics of galaxies that indicated dark matter. Vera Rubin was one of the pioneers. And then eventually it was realized that the universe as a whole has a lot of dark matter in it from observation of the cosmic microwave background. When we analyze the anisotropies, the fact that the microwave background is a little bit hotter in some directions than in others, we can explain it, and the explanation involves dark matter. So as of now, there is a standard cosmological model. There is plenty of data that we have accumulated over the past few decades, and all this data is consistent with a standard model for the universe. And one of the essential ingredients of this model is the existence of dark matter, some additional constituent of matter that makes up more than 80%, more than 4/5 of all the matter in the universe. And it's not interacting with light, so we can't see directly. And the fundamental question is, what is it? And the most popular view is that it's made of particles, just like other types of particles, but these particles interact very weakly with radiation. And so that's why we can't see those particles. And we hope to at some point detect them directly. So there is a lot of work on building laboratory experiments that are extremely sensitive and could, in principle, interact with these particles. There is also an attempt to constrain the existence of these particles in colliders, like the Large Hadron Collider of CERN, where particle beams are colliding, and there is a possibility that dark matter will be produced in these collisions. And again, the answer is no detection as of yet on both fronts. And for decades, people were hoping that there would be some signal, and people were forecasting or making prophecies that by now we would definitely know what the dark matter is. But despite all these experiments on Earth, we haven't found any clue, any signal from the dark matter as of yet. And so the question then is, could we use the universe to probe the dark matter, the nature of the dark matter, in a way that is not gravitational, in some other way? And that's where the EDGEST result comes in.
Yeah, I want to get to those results in just a minute, but I did not know that you could actually try that there are efforts to try to see dark matter from CERN. I know that there's observatories out there. I think they use xenon gas or something to try. Right. These observatories are trying to detect a dark matter particle as it somehow, and I don't understand the physics.
Well, Cora can comment on that.
Okay, maybe just a brief comment on those observatories. How are they trying to see dark matter
so
there?
These are so-called direct detection experiments. So what they are trying to measure is they're generally deep underground, and what they are trying to measure is if a dark matter particle hits the detector, then they would measure the nucleon recoil of this.
The nucleon recoil?
Right. So how the detector reacts to the momentum and the kinetic energy coming from a dark matter particle, how the ordinary matter reacts.
Oh.
And
there is a kick to a particle in the matter, in the ordinary matter, as a result of this impact.
I see, but I guess go ahead, Cora.
Yeah, by not observing this is what Avi was referring to. By not observing this kick, they put strong constraints on what we thought should have been detected by now. We haven't seen yet. So what we are starting to rule out is huge portions of the so-called parameter space. We call parameter space to a space of possible parameters that characterize the physics of the physical properties of dark matter.
So even though dark matter doesn't interact with normal matter in any detectable way, somehow in this xenon gas, it produces a kick that has not been observed. It's what you call the nucleon kick, I think you said it was. And that since that has not yet been observed, and it should be if dark matter is what we think it is, then that puts constraints on what dark matter isn't, right? It tells you what isn't a property of dark matter. Okay.
The way I would phrase it is, what we thought dark matter is this famous WIMP, weakly interactive massive particle.
Right, WIMPs.
Right, and the WIMPs do interact with us slightly more than gravitationally. This type of interaction is weak, like weak force. That's where the name comes from. And you would expect some recoil from these interactions with nuclei. But we don't see this recoil at all in any of the experiments that have been looking for it. That is why we think it is not a WIMP, or if it is, it has to be a very weird WIMP.
A weird WIMP, a W-WIMP. Okay.
By the way, we should mention also that in addition to WIMPs, some people suggested that the dark matter is made of machos, which is the opposite to WIMP.
Of course it is.
Macho is an abbreviation for a massive, compact halo object. I mean, the dark matter fills the halo of the Milky Way. And one possibility is that you have objects like stellar mass objects making the dark matter. For example, you can imagine primordial black holes that were produced in the early universe. And, black holes are black. They don't interact with light. They are extremely small. And so they would appear as dark matter. If you have enough of them, and some people recently suggested that maybe even the LIGO event, detections of gravitational waves from the collision of two black holes, maybe those black holes came from the dark matter. Some people suggested that. So that's a possibility. There are issues with this possibility, how to make exactly the right amount of dark matter. It's very fine-tuned. But nevertheless, there is this possibility of massive compact halo objects, machos, and that was ruled out by experiments 2 decades ago that looked for gravitational lensing, basically focusing of light from background stars by those machos. So when a macho passes in front of a star, it acts as a lens. It focuses the light, and you would see it as a temporary brightening of the background star. And people looked for those brightenings and could set very tight limits on the population of massive compact halo objects. And they ruled out the possibility that the dark matter is made of those. And so, but people still consider other types of compact objects not having roughly the mass of the sun, but maybe much less than that, the mass of an asteroid. There is some parameter space left, but most of the community believes that it's probably elementary particles. It's not a compact object.
Okay, good. Well, we set the stage a little bit for dark matter there, folks. It amazes me that how much we can learn about dark matter just by seeing its effects on things that we can see, like the rotation rates of galaxies. I remember when I was at the Space Telescope Science Institute, the Frontier Fields project had lens models of the Frontier Fields galaxies in such a way that included dark matter and where it was. It just astonishes me that we can not only say that it's there, but also we can get rough maps of where this dark matter stuff is in and around galaxies, and it really is quite astonishing what we can learn. So the confidence rate is high, I think, that dark matter is there. The alternative, I think, is this MOND theory, but I don't want to get into it now, but it's this idea of modified gravity at large scales. But I don't want to get into that because I want to talk about the research here. So let me pull up this graphic that many of you have probably seen. This is a history of the universe, a graphic that NASA produced, and it shows the whole history of the universe. Now, this experiment, the EDGES experiment, which stands for Experiment to Detect the Global Epoch of Reionization Signature. Again, I'm not apologizing for this acronym, but it is a weird one. It is looking at a part of the universe. And Julian, maybe you could give us an update or a little description of where in this graphic we are looking, where EDGES is looking, I should say.
So if you go here, you go from left to right, you go to later times in the universe, right?
That's
so
right.
On the left, you can see where the CMB is, says afterglow light pattern. That is a cosmic microwave background, the CMB, that we all know and love. And you see that right to the right of that, there's an epoch called the Dark Ages. This is called Dark Ages because there was no source of light. The cosmic microwave background had just been emitted, and no stars had been formed yet. So the universe was mostly neutral hydrogen, and it was very, very dark. But you see that this ends when the first stars are formed. It says about 450 million years after the Big Bang. This is the era where EDGES has detected the first signal of 21 centimeter. It's in the cosmic dawn, which is how we call the end of the Dark Ages, when the first stars in the universe are formed.
About 400, it says about 400 million years down there at the bottom. So this is an area known as reionization, and without going into too much of the nitty gritty on this, there was this is where the I'll go ahead and put this up. We'll try seeing how this goes. This is an animation that shows what reionization is. The very first stars were very hot, and they let out a lot of ultraviolet radiation, blasting out these cavities that actually stripped some of the neutral hydrogen that was in the universe from its atoms, ionizing it again. Am I getting that right?
That is right. That will happen later.
What will happen later?
So the reionization. So the Big Bang, stuff is ionized, then it goes dark because it's expanding, and then stuff forms, stars form, put out light, then ionizes again. So that's why there's dark ages, and that's why it's called reionization, because it was ionized,
it happens
then not, then reionized.
Okay, good. Good. Okay, thank you. So
that's the idea.
So there's the stage for our research. So the EDGES Observatory is a radio telescope that looks at this period in cosmic history. It's located in Australia. It's just one telescope, and so let's go ahead and get to the basics of your paper, Julian. Maybe you could give us a...
Could I just interject one question?
You may.
So during the Dark Ages, so we have this period of ionization, then we have Dark Ages, and then we start to form stars and galaxies and stuff. What's the dark matter doing?
So that's extremely important because without dark matter, we wouldn't exist, okay? The ordinary matter, actually on the scales of galaxies, is very smooth to start with. The dark matter, because it doesn't interact with the radiation that fills up the universe, it doesn't get smoothed out. The radiation is smoothing out the ordinary matter. So the dark matter keeps memory of the initial inhomogeneities, and then it starts clumping on the scales of galaxies. If the dark matter did not exist, we would never exist. So we all are existing. If we go back in time and ask where our roots lie, our roots are in these inhomogeneities that the dark matter had on very small scales that ended up collapsing to make galaxies like the Milky Way, inside of which stars like the sun were made.
And that's because the dark matter acts gravitationally on the normal matter, but not with the light?
Yes, it brought it together with it. And there would not be this collapse, this condensation to make galaxies like the Milky Way without the dark matter keeping memory of these initial inhomogeneities from place to place, because the ordinary matter forgot about those initial conditions because of the radiation that fills up the universe. The amplitude of the perturbations was extremely small on the scale of galaxies.
I'm sorry. While you're talking, Avi, I'm going to put this graphic up from Julian. If you look at the far left of this, you could see the cosmic microwave background. Those little inhomogeneities you're talking about are the red and blue granularities, right?
Right.
Okay.
And that's mostly due to the dark matter. But what we're seeing here are very large scales on the sky. I was talking before about the scale of galaxies, which are much smaller than these scales we see on the sky.
Oh, okay. I misunderstood.
And on those scales, the radiation is very smooth. So if it's basically, we're talking about a scale that is much smaller than a pixel in this image that you have on the left. And there you get very smooth radiation. However, the dark matter is still clumpy on those small scales, and that's why you make galaxies. So the process starts from the dark matter clumping and attracting together with it gas. And that's what leads to the formation of the very first stars about 100 million years after the Big Bang.
So one other question, and I'll let you talk about your paper and the charges. So the dark matter, I don't know anything, this isn't my field. My field is like stars, and star clusters. Anyway, so does the dark matter make the cosmic web?
Yes. The cosmic web
influence the making of the web?
When you say making, it's the dark matter is the dominant constituent in the universe in terms of the matter in the universe. So when matter clumps due to gravity, it's mostly dark matter. And so when you talk about gravity, it's dominated by the dark matter until you start making galaxies. And then what happens is the ordinary matter cools and it settles to the middle of a galaxy. And it settles usually to a disk configuration because eventually it rotates around the center in a disk. That's why the Milky Way looks like a disk. And that's why the stars formed in the inner region of the Milky Way after the gas cooled. So you need, in order to make stars, you basically need to make a galaxy, make a collapsed object for which the dark matter is the primary agent. That's the reason that we have galaxies, the dark matter. And then you need the gas that comes together with the dark matter to cool and condense in the center to high enough density such that stars can be made. And for that, you need to cool the gas. Now, what we are talking about in the dark ages is most of the gas is still not collapsed into galaxies. By today, a significant fraction of the gas went through galaxies and came out. But back then, the process of galaxy formation just started, and it starts on small scales. And then it's hierarchically growing. Small clumps combine to make bigger and bigger galaxies as time goes on and more matter falls in. But early on, most of the gas was relatively smooth. And the question is, what happened during those dark ages? How cold did the gas get before it was warmed up by X-rays from accreting black holes and so forth? And I will let Julian describe it. Basically, what Edges claims is the gas was much cooler than allowed by just the cosmic expansion. So Edges argues that somehow the hydrogen got cooled below the floor that we allow for due to the cosmic expansion. And then the question is why? How is it? Is there another fluid that is cooler than the gas? Well, yes, there is the dark matter. So if somehow the gas could couple to the dark matter, it could get cooler than we expect it to be.
Okay, I want to get
now
Julian.
We know that landscape in the dark ages. Okay, and what the relationship is between the luminous matter and the. Okay, so Julian.
Okay, yes, I want to. So yeah, let's go ahead and get to his paper. I want to put this up as the first slide that you sent. Maybe you could use this as a backdrop for describing in a little more detail what your paper found, what the observations were from Edges.
Right. So here, I'm going to first describe what Edges saw and what they expected to see. So, as I said, the cosmic microwave background is emitted at very high redshift, very early in the history of the universe, and is what we call a black body, which means has photons of a lot of different frequencies. So we expect, given that we know the temperature of the CMB, which is the famous 3 degrees Kelvin, we expect how many photons to see at every frequency. So this is what we have, this intensity, this I nu goes as the temperature times frequency squared, nu squared. Now
That's
these photons,
this here? That's this here?
That is right. So
okay.
you know how many photons are emitted.
Okay.
Some of these photons on the way to us, they cross hydrogen. And hydrogen has a ground state that has different spins for the proton and the electron.
This is neutral hydrogen.
There's neutral hydrogen, that's right. So this is before reionization. So some of these photons will get absorbed, and you will see less photons on the other side.
That's right. More photons, less photons.
Right, and how many photons you're missing, that is what edges will see on Earth. So this thing on the right is a cutout of a little picture from the experiment itself. So you see it's a metal plate, because radio experiments, radio telescopes don't look like normal telescopes, don't have mirrors and stuff, because you're looking at things that have frequencies of order meters, or wavelengths of order meters. So you will actually just need a metal plate to be able to detect it.
And you said that edges sees what didn't make it through the hydrogen?
Right, edges can roughly count photons. They can count what is the intensity in photons that they see, and they should be able to tell how many photons they're missing with respect to the expectation.
Oh, okay. All right. Because we know we have a familiarity with the CMB. We know what it should be emitting and what it is emitting, and then what we actually see, and the difference is what was absorbed.
That is right.
It's similar to looking at the 100-watt light bulb through some fog. Imagine some dense fog, and you don't see the full 100 watts. You see less than that.
But you got a 100-watt bulb, and it should be so bright. I get it. And then so by seeing how bright you actually get, you're getting how much was absorbed by the fog.
That's right. So if you look at the next slide, that is actually what they reported. That is what they showed in their Nature paper. So here, this T21, the y-axis, that is roughly what is the temperature that you have absorbed. So because the original temperature is like 3 Kelvin for the CMB, you see that they have absorbed about minus 0.6 Kelvin. So this is telling you that 0.6 out of 3, or roughly 1/5 of the CMB photons is missing.
And this this is plotted as a function of the age of the universe.
It's a function of redshift, yeah. So you can think the redshift 20 or so is when the first stars in the universe were formed.
Right. And so this dip that we're looking at was greater than what people thought?
That is right. So you look at the green dotted line.
Yeah.
At about minus 0.25. That is the maximum absorption that is possible. Not like the normal amount we would expect. That is the maximum absorption possible within the standard model. If you want to go below that, as the data seems to
this goes a lot below that, doesn't it?
Yeah, a factor of 2.
Wow. So I guess I don't. The standard model is saying the green dotted line is it. That's the most that dip should be there from the first stars in the universe, and yet you've got this much bigger one.
But we should keep in mind that the extraordinary claims require extraordinary evidence.
Okay.
Speaking as a conservative old professor,
Well, the press release was a little funny about this. It was like, this still has to be confirmed, and this is kind of controversial.
Right.
So
So
I guess,
one has to be careful because this is the first claim detection. These are extremely careful experimentalists that claim that. Alan Rogers and Judd Bauman, and they are very trustworthy. But it's still possible, they might have detected an absorption signal, but it may have originated from something else, not from the cosmic dawn, but from some other intervening source of radiation or source of absorption or whatever. So we have to be careful. This is the first thing that needs to be done is to have another independent experiment with a completely different set of hardware and systematics that gets the same answer. Yeah. That's the first thing.
In fact, there is.
Go ahead, Corey. No, go ahead, Corey.
But then, of course, there are additional predictions that Julian and Cora and I made in a follow-up paper that could, in principle, be looked for. And those predictions, if confirmed, will definitely solidify the validity of this interpretation that indeed the hydrogen is cold. So that different way. First, something needs to be confirmed by an independent experiment, but also there are additional predictions for how the signal would vary across the sky that was not measured here, because here the radio antenna is just summing over the sky and measuring the average, the sky average absorption. But in principle, you can look for the absorption at different portions of the sky, and our paper predicts how that, how much variation you would get for that. And that is really very sensitive to the reported signal.
Yeah, I wanted to second what Avi is saying in that, in fact, so I agree that this is, it's an interpretation of a signal that possibly is real, but possibly is not real also. So we need to confirm it. There are experiments. In fact, there is one from a local person called Lida at MIT, actually, trying that should be able to confirm the signal or not, or rule it out. But as Avi is saying, if this signal is correct, and then if this interpretation is correct, there are possible predictions that one can make for the fluctuations on top of this signal. And by the fluctuations, I mean the fluctuations on top of the absolute signal, the same way that we have fluctuations around the 3 Kelvin temperature of the CMB, we could have fluctuations in this
in the fluctuations
brightness temperature.
Okay, so these are controversial results. They need verification, and you guys have outlined ways not only to verify that this is true, but also what to expect if you look in different parts of the sky.
I should say that they deserve 2 Nobel Prizes if it's real. There is one Nobel Prize for being the first to detect the absorption signal from cosmic hydrogen during the cosmic dawn, which is a major milestone. It's a major discovery. And the second is, if the signal is correct and indeed the gas is cooler than expected, there needs to be some non-standard physics responsible for that. So there is some new physics here, and maybe potentially related to the dark matter, that is responsible for the signal. So that's the second Nobel Prize. So that's why one needs to be really careful at verifying the signal, because if it's real, it's really important.
It's a big deal. Well, let me sort of segue from there into the paper on the electric charge. So controversial as all these observations, and still yet to be verified, you guys didn't stop. You said, wait a second, okay, what if this is dark matter interacting with this, causing these, then what would make it do that? And you guys put up a model. You guys started modeling things. Who wants to tell me about the model? Yeah,
so I can tell you the rough picture of why we're caring about dark matter interactions, and this, we don't just say it's impossible. So the reason is, this cosmic dawn is the era of the universe where the baryons, which is the hydrogen and the regular matter, and the dark matter, have the slowest relative motion with respect to each other. So what this is telling you is, if you have some sort of interaction that is more important where the two fluids are slow, it will show up here first. Before it shows up in accelerators, before it shows up in any other cosmological observation, this is the era where it would show. And it just so happens that interactions with an electric charge, which, the typical Rutherford interactions that you have between nuclei, those are more important at low velocities. So that's how we started getting into charged dark matter. Okay, so that adding a charge to the dark matter helped explain these observations, but there's a hitch in this, as I understand it. You can't just say all dark matter has a charge, that's right. Because then that throws off stuff in the current universe, right? So explain that a little bit. It can't all be charged. That's right. So not all dark matter can be charged. There are many ways why we know this is true, but one of the simple ones is, we know that charged particles follow magnetic fields. And magnetic fields are present in a lot of astrophysical environments. So in neutron stars, and in particular, they are in the galaxy, in our own galaxy. So the dark matter in our galaxy wouldn't behave like cold dark matter like we're used to. It would follow magnetic fields instead. And we know that it doesn't. So we can say that not all of it. Certainly not the dark matter that's in halos around our galaxy and others like it. It's not following the magnetic fields. Right, not all of it, at least.
Right.
Because you're right that we can actually find where dark matter is through gravitational lensing. We can get maps of dark matter. This is something you touched on before.
Mm-hmm.
But these maps have like fairly large error bars. So
do they?
there
Okay.
can be some fraction of dark matter, say 10% or so, that could actually be in some other form that we, wouldn't show up in these maps.
Well, how much then? What do you have a percentage, an idea of how much should be charged versus how much is neutral? And this kind of seems to me like, wait a minute. Now not only are we not sure what dark matter is, but we're not even sure how many different kinds there are now. Because now we've got neutral dark matter, we've got charged dark matter, we've got WIMPs and maybe not machos and maybe not even WIMPs anymore. So what does this say about, do you have a sense of how much of this, based on these observations from edges, might be charged?
Good.
One comment, Julian, just to clarify. So when we say that only a small fraction of the dark matter may be charged, it could be a situation quite similar to the ordinary matter. When we have atoms in the early universe and only a small fraction was broken atoms, ionized or charged particles, free electrons. So you can imagine the same situation in the dark sector, that you have these neutral particles making most of the dark matter, and only a small fraction are broken into charged particles. And the other thing to keep in mind is what we call dark matter could be a soup of different particles. And the question is, what's the composition? Which fraction is one sector, which fraction is another? And there is no reason to suspect that it's only, that the dark matter is only one set of particles. That is too simple. When you eat soup, it's not made of just one broth. It's often a mix of things.
Well, you bring up a good point, because even in reionization, just because reionization was happening, it wasn't happening to every single atom in the universe. Some things did not get ionized. There was plenty of
early on, only one part in 10,000 of the atoms were ionized early on, before the first stars.
I'm sorry, how much? 1/10?
1% of a percent.
Oh, wow. Okay.
So if we say 1% of the dark matter is charged, for the ordinary matter, it was 1% of 1% was charged before the Dark Ages. So, it's even more fine-tuned.
So analogous to the standard case, in this case, we would have dark atoms.
Right.
And notice also that you get reionization in our side, in the visible side, because there are stars. There's no reason why you would expect dark stars to exist, and then there will be no UV photons or dark photons. And that, this 1% would stay for the rest of the universe.
Wow. Okay. So, I want to get to some questions here, but we're about 40 minutes in, and I think it's time, Carol, for us to maybe talk a little bit about our Hangouts and remind people why we're doing these and things like that. So can you say a few words about those? You're watching an Astro Coffee Hangout.
Yes, Astro Coffee Hangout is supported by the American Astronomical Society and the American Astronautical Society, scientists and engineers. And the idea is to have informal chats with people doing the research. We, at our home institutions, are used to having science coffee, having an informal talk, and then a colloquium if somebody is a visitor. But we thought it would be interesting to share with everybody by talking to the people who are doing the research that you see in the news and we see by reading the refereed publications, like what are they doing, what motivated them, what's the background. So that's why we decided to do Astro Coffee. So welcome.
Yeah, and I want to thank both of those organizations for supporting this. Okay, so let's get to the meat. I want to get to some questions here, but before I do, Julian, did we cover most of the topics in your paper, the big picture items? The fact that these observations from edges produced some strange results. One possible explanation, they need to be verified, is that dark matter could have a charge.
I think something that we should expand upon a little bit, perhaps, is the idea that not only this would explain the edges result, but even if the edges result went away, and even if disagreed with some expectation that we have, this would place constraints on what dark matter is and isn't.
It gives us constraints on what dark. You cut out a little bit. You say it gives us what dark matter is and what it is not. Is that what you're saying?
That is correct. Exactly.
You're getting a lot of constraints on what it isn't. I sure would like to know what it is. Okay, let me get to a question from Joe Schmoe. And by the way, I guess there was some problem early on in the Hangout about the YouTube chat. I wish I could control it. I hope that you're able to get on to the Discord chat. I'm not seeing a whole lot of stuff there, but apparently it seems to be worked out because I'm seeing activity on the chat now. I can't control YouTube, guys, so I don't know what's going on. Joe Schmoe, is there a relationship between the distribution of dark matter and the location of larger supermassive black holes?
Well, so first we should explain that supermassive black holes are found at the centers of galaxies, mostly, and they are thought to be the result of ordinary matter accumulating there, sort of like water collecting down the drain in a bathtub. And so ordinary matter collects at the center of a galaxy and often makes a black hole there. And we see those black holes, they make up about 1/10% of the amount of ordinary matter that you find in the cores of galaxies. Okay, and then if the formation has nothing to do with the dark matter, then you would think, that there probably is no link between dark matter and supermassive black holes. But the point of the matter is that there is more ordinary matter in galaxies that have more dark matter. So the bigger the galaxy is, the more ordinary matter it collects, and therefore the bigger the black hole that it makes. And we do see this correlation. We do see that bigger galaxies have more massive black holes at their centers.
Okay.
But it's not because there is any interaction between the dark matter and the black hole.
Corey, you're nodding your head. Did you want to add to that, or is that?
Yeah, I agree with what
Okay,
Abby
all right. Condor Boss is asking how, this is going back to the recoil and the measurement of dark matter particles in those observatories. How would the recoil from dark matter be different from a neutrino interaction? Because neutrino observatories, I think they use something, another liquid water maybe, I'm not sure what they use, but how would that recoil be different? Anyone?
You want to get it, Cora? Or?
Cora?
Sorry?
The recoil from dark matter that are being used in observatories to try and find dark matter, how would that be different than a neutrino interaction?
So that's why these experiments are built deep underground. So we have a lot of backgrounds from high energy photons or other particles that could be hitting the detector, and we could in principle think that it's hitting by dark matter. But that's why we try to shield these detectors to avoid other particles, up there that could be also hitting the detector that are not dark matter.
Now, the other thing to keep in mind is in terms of neutrinos, we know what to expect. So we know what is the neutrino background, more or less. That was calibrated. And also the neutrinos that we often detect are different energy and momentum of kicks than the dark matter. So there is an imprint, a fingerprint of the dark matter, because we're talking about massive particles, particles more massive than a proton, typically. That's what people constrain. And the impact from such a massive particle that is moving, at a speed much smaller than the speed of light. These are non-relativistic particles. The impact, the recoil, the properties of the recoil are quite different than the recoil from a neutrino, which has very little mass and comes with a lot of energy, and usually has altogether a different amount of energy than the dark matter particles have. So we can tell by the amount of energy that the recoil carries, we can tell whether it's a dark matter particle or a neutrino. And by now we calibrated the neutrino background, so we pretty much know what to expect.
You can just remove that signal.
The rate of such events. Yeah.
Okay.
Yeah.
Cool.
In fact, these are called the backgrounds of the experiment because it's not the stuff that they are looking for.
Well, okay. Tashin on Discord is asking, question for the panel. What are the ramifications of this theory being proven? What would change about the research and observation of the cosmos if this turns out to be correct?
Well, there is go ahead, Julian.
I was going to say something that would be really interesting is that you would not expect 1% of dark matter to be charged in isolation. As we talked about before, you would expect some sort of dark atom to make up the other 99% or something else that is neutral. And then these particles we can actually talk to because they have an electric charge. And they would give us a new window into the whole dark sector that might be very complicated. So some ramification would be that if this was actually the dark matter, we should be making a lot of effort to try to produce it in laboratory with accelerators or similar things.
Back to CERN then, maybe, and something like that. Okay.
But also, there is a fundamental issue here that if we couple the dark matter to electromagnetism, that has some deep implications to the standard model of particle physics, because electromagnetic interactions, for example, just to give you an example, neutrinos are not expected to have a charge, and they are not expected to interact with electromagnetic radiation. And so that would say the dark matter is fundamentally different than neutrinos. And if it has a charge, why is it so small compared to the electron? All the charges that we found until now are multiples of the electron charge, and integer times the electron charge. And why is this a fraction, such a small fraction? There are many. This will definitely inspire a lot of work, both theoretical and experimental, as to the
my God, I didn't even think of that. That's right. The standard unit is the electron, right? And so this is if this is some fraction of that, then we've got some issues. Wow.
Well, issues or benefits. I mean, you can imagine.
No, it's issues. I need therapy already with dark matter.
Well, the question is whether it can be used for any practical applications like communication, or can you use dark matter for that? If it interacts electromagnetically, that would be interesting to think about.
Very good point. Okay, John Suffel is asking, what about anti-dark matter? And then Condor Boss responds, anti-dark matter, I think we need to define the regular stuff first. Amen, Condor Boss. My head already hurts with this. Don't be talking about anti-dark matter. And Condor Boss is also commenting, there's definitely a Nobel Prize waiting in dark matter. That's interesting. I didn't know, by the way, when you commented that on Avi, that is such an important, this could be such an important discovery.
Yeah, but we should keep in mind that there is something more important than prizes. I mean, the Nobel Prize is nice. It comes with a financial benefit, but it's really understanding nature that drives us all. We are not in it for the money. We're not in it for the glory. We're in it for figuring out what nature is all about. I think that's what you find as the common denominator among most scientists. And, it's the curiosity that we want to figure out what our roots are, what is the environment that allowed us to exist. And the dark matter is such an important constituent of the universe that we cannot ignore it. And we need to find out, because as I said before, our existence is tied to the dark matter. It's sort of like figuring out who your grandparent was, like going to archives and finding out, how your grandparent looked like. And so for us, figuring out the dark matter is really an existential search. We want to figure out how we came to exist.
Okay. Well, that was very humbly said, by the way, about the Nobel Prize. So, I just lost the question I was going to ask, so I'm going to ask this one. This comes from ASCII on Discord. Does our present knowledge about the huge number of planetary systems change the amount of real matter versus dark matter that was once estimated? That's a good point. I want to just interject my own little thought on this, and that is that we always say that everything we can see in the universe, stars, galaxies, everything that we can see, feel, touch, smell, taste, is about 5% of the universe. 20-something odd percent, depending on who you talk to, is dark matter, and the rest is dark energy. So we come along with Kepler, the space telescope, and it tells us that, wow, you know what? There's about, on average, 1.6 planets around every single star in our galaxy, on average, and we didn't see those before. So is this matter that's all included in the 5%, or is this some new matter that we didn't know? So The question, in the spirit of Askey's question, and I think where you're going is, when we discover new things, does that change the 5% part of the amount of stuff in the universe?
No. So the point is, at first, people in the early days, I'm old enough to be of the generation that didn't really know how much dark matter there is to start with. That was like 20 years ago, 30 years ago. And so back then, some people suggested that it was all ordinary matter to start with after the Big Bang, and then a fraction of the ordinary matter may have gone into dark matter, like you can make compact objects, for example. But that is ruled out because we have additional constraints from the early universe. For example, it's called Big Bang nucleosynthesis. That's where the light elements were made. We measured the abundances of light elements, and we measured microwave background. All of this information tells us that the dark matter is 80% of matter in the universe. So you can't just take the ordinary matter, convert it to dark matter. It's not allowed because the ordinary matter couples to the radiation and dark matter doesn't. And we know that most of the matter could not have coupled to the radiation from very early on in the universe, And so we know it's some other stuff. There is the remote possibility that maybe there is no stuff there and it's only modified gravity. Gravity is behaving differently than we think. But that by now is, very difficult interpretation because we have constraints from so many different experiments on the dark matter that it's just, there is no modified gravity model that can explain all of them in a simple way. I mean, the modified gravity MOND, for example, explains what happens in galaxies, but what happens cosmologically is not yet accounted for at the level of precision that the experiments are delivering. They deliver 1% precision now on cosmological constraints. We are at a time where the cosmological tests are at the level of 1%. And the standard model where the dark matter is some stuff, some matter, and it's not modified gravity, that model stands up to all the tests to a precision of a percent level.
Wow, that's a good answer. Did you want to say something, Julian?
Yeah, let me come at this question from the orthogonal side to say, even if you added all the mass of all the planets that come around every star, it's very, very small compared to the mass of the star itself, which we already need.
Right.
So you can take all the planets in the solar system, you add up their masses, and they are not even 1% of the mass.
Right. It's about a tenth.
Yeah, but also we hear about discoveries all the time. Just this week, in fact, I think just today I read about astronomers saying the Milky Way is way bigger than we thought it was. So these new discoveries that say more planets are out there, more galaxies are bigger than we think, really all of it is constrained in what Avi said. In the early universe, the cosmic microwave background, I forgot the term. Nucleosynthesis. Thank you. All of it, that constrains how much anything the visible matter can be. So all of these new planets, all of these big galaxies is all still got to fit in that 5%. It doesn't change that number any. Yeah, and you're right about the planet part. It's the percentage compared to the star is quite small. But I just read about the Milky Way being bigger than we thought it was, so there's more stars.
One way to put it is that if you worry about your weight, you can't gain more weight than the amount of food that you eat. Okay, and so
thank God.
So if you weigh the food and then you eat it,
conservation of food.
That's the maximum you can gain. And the same is true about planets and stars. They can't consume more than is available in ordinary matter, which is 5 times less than dark matter.
Okay, Joe Schmoe wants to know, are unbound gravitons a candidate for dark matter? Unbound I don't even know what those are. Do you know what an unbound graviton is? Graviton is apparently the particle that transmits the gravitational field, maybe?
Let me say, I think he means gravitons gravitons as in like the carriers of the gravitational force.
Yes.
And we know these particles are massless because gravity goes to very, very far distances. Massless particles cannot be the matter. Dark matter has to be fairly heavy so that it can fall into halos, like Avi was saying before. Because if dark matter was like radiation, it would never form these galaxies on which the regular matter can form stars.
Okay, so Condor Boss, reionization, is that like Coke Zero? Yeah, it tastes better. Okay. Dark matter. Let's see. Is there a relation? This is from Joe Schmoe again. Is there a relation? Oh, I already asked you that question. Sorry. Okay. Okay. He also wants to know about the relationship between dark matter and black holes in the model of galaxy formation. So, how does dark matter fit in with galaxy formation? You have 10 words.
As we were discussing before, most of the matter in the universe is dark matter, and there are variations in the density of dark matter from place to place, and so regions that are denser than average eventually collapse upon themselves to make galaxies or bound objects. So the dark matter is basically dictating that process because it dominates gravity.
Yep. It also
and then the ordinary matter follows.
Okay. Andrew Planet is asking, hi Andrew, it's good to see you again. If dark matter has a charge, could that be a signature of it being aligned in some way so as to allow for that charge? I'm not. Maybe he means following field lines. If dark matter has a charge, could that be a signature of it being aligned in some way so as to allow for? So I think we don't know enough to really answer any of that because.
Now I get it. It probably means if there are magnetic fields, then charged particles are allowed to move in the direction of the magnetic field. So there would be some, organized way by which the dark matter would flow, which depends on the magnetic fields, or it would carry the magnetic field with it. That's what happens to ordinary matter when it's charged and there are magnetic fields. Usually the magnetic fields are tangled, and so you end up with a behavior that is very similar to a fluid. That just in a regular fluid, a particle bumps off other particles and then its trajectory gets deflected, and that's what makes it a fluid. That all the particles are moving together because they bump against each other, just like billiard balls. So the magnetic field can serve the role of collisions because the dark matter particle trajectories will be deflected by this tangled magnetic field, and it's true. So the dark matter would behave more like a fluid if it were charged. So the charge component of the dark matter would be affected by the magnetic fields. Yes,
and that's kind of what we were talking about with if all dark matter had a charge, that kind of throws off what we see in the present universe around galaxies. Right. Yeah. Okay. Simon Farmer is saying not to downplay your instrument. It did seem like it was small, right? But is it small enough that it seems like someone else should be building an independent version? And is that happening? So it did seem pretty simple, right? It was a relatively small and simple device.
Yeah, actually, I should comment that the budget of this experiment was rather low. We're talking about hundreds of thousands of dollars, which is a typical NSF grant kind of budget. This was a low-budget experiment, and additional experiments can be done with proper expertise, and they are done. There are at least two groups that are currently, pursuing a signal. One was mentioned by Cora, LIDA, which is led actually at the Center for Astrophysics here at Harvard by Lincoln Greenhill, and then there is another experiment in India called SARAS-2. SARAS-2, which again tries to measure the same signal. So these are two ongoing experiments, but there is something also on the horizon. It's called HERA, which will try to map the absorption on the sky. So basically look for variations in the level of absorption across the sky.
And they would presumably use those predictions you were talking about earlier in your other paper. Exactly. I see. Good. Well, that's good to know. So this is something that it sounds like work is being done on verifying and duplicating.
Yeah, definitely. I mean, scientists are reasonable people, They do what they can.
Well, also, when you have proposals like this, theorists immediately go to work and, observational lists dream up ways to observe. So it starts the whole new industry.
But I should mention that observers are the only ones that do not believe data. I mean, theorists believe data much more easily than the observers. Vice versa, the observers believe theories.
But
you know what Yogi Berra said once? Yogi Berra said that in theory and practice are the same. In practice, they are not.
Okay. I was.
I take your point.
With the I got time for maybe one more question, and I just scrolled through it, and it had to do with because we well, I'm going to paraphrase. I'm sorry, it scrolled past, and I don't want to spend a lot of time looking for it. But the question, the essence of the question had to do with, if this has a charge, then could the implications of maybe, are there? And I think you were commenting on this early, Avi. What could that mean for maybe technology and maybe making motors or things like that out of?
Well, that's an interesting question. For example, we didn't mention that, but in addition to the dark matter, there is dark energy in the universe. We didn't talk about that, but that's like the vacuum. If you remove all the matter, there is the vacuum left. And in quantum mechanics, the vacuum can have some mass density, uniform. And that is causing the universe to accelerate its expansion, actually. And there was a Nobel Prize for that. And we don't understand the nature of the dark energy either. So there is the dark sector. But for example, the Department of Energy is funding research on trying to understand the nature of the dark energy and the dark matter as well. And you may ask, okay, why put federal funding if it's not clear whether there would be a use for it? And the answer is that in the history of astronomy and cosmology, there are many things that were done just for the sake of understanding things better that ended up being very useful practically. Just to give you one example, GPS systems that we use in cars and so forth, they reach the precision that we need only thanks to Einstein's theory of relativity, general relativity. And that was developed just to allow consistency between special theory of relativity and gravity. And so it was developed just to describe the universe at large, ended up being very practical in our cars, And so it's useful to try and to your question, we don't know really how to, we cannot excavate the dark energy and make something out of it. And we cannot yet use the dark matter for anything. But if we understand it, perhaps we will.
I know we're out of time, and I just want to get this one question in before we run, because it's a good one. This is from Professor Master's class in Haverford, and I'd love to know the answer too. Why wouldn't a charged particle emit radiation? I mean, we all know if you take a charged particle and you accelerate it, you get radiation from it. So what about that?
That's a very good question. So what happens is these charges are so small that the amount of radiation you emit is entirely negligible. You can think of it this way. We know that both electrons and protons emit radiation, right? However, in astronomy, we only almost see electrons because the protons are much heavier. So the charge to mass ratio is about a factor of 1,000 smaller than the electron. So even though the protons are emitting, they are entirely negligible compared to electrons. So these particles are even less charged, so they're even more negligible than protons.
So they are radiating, you just can't see it.
It's
too small.
Because we are talking about 1/1,000,000th or less of the charge of an electron, which was mentioned before, but just to...
Yeah, so good. All right, well, I'm going to leave it there. Guys, this was an outstanding paper. Thank you so much for taking time out to explain it to us and to share it with us. I hope these other observatories are able to confirm these findings or these observations from EDGES, and if there's more coming out, I hope you guys will consider coming back and giving us an update. I'd really appreciate that.
A pleasure.
Okay, well, that is it for this episode. Next week we are going to be back with Future in Space Hangout with Harley Thronson, and we are going to be talking about a space gateway that is being built or being considered by NASA. So that is next week. Also, on Wednesday we're having a hangout on the history of astronomy with a professor who's going to hit some great topic or ideas on the very first astronomer. So we'll be talking about that next Wednesday. So if you want to be notified of, please like this video, by the way, share it with everybody, help us spread the word that these are out here. We are here for you guys. This is your chance to interact with professional astronomers. And so we want you to take advantage of it every Thursday at 3:00. Please like this, share it, and send it around. If you want to be notified of when this stuff goes live, when new stuff comes up, if you just leave your email address at deepastronomy.space, I promise that's all I need. I won't take any other information. You can be notified, and I won't share your email address with anyone. So please take some time out to do that. On behalf of Carol Christian and my guests that were Dr. Avi Loeb, Dr. Julia Munoz, and Dr. Cora Dvorkin, all from Harvard University, looking at charged particles, looking at the possible charge of some dark matter. Thank you guys very much, and as always,
thank you. Yes, thanks for joining us. This was great. Thanks.
Yep. Thank you for watching, and as always, keep looking up.
And have a good summer.
That's right. Bye-bye.
Bye.
Thanks for inviting us.
You.